One of the strange things about black holes is that if you were to cross the event horizon, you could never return to tell anybody what was inside. The reason is not so much because of the strength of the gravitational pull, which may not be that strong for a very large black hole. Rather, it is because of how the curvature of spacetime affects your motion through it. Once you cross a black hole event horizon, your light cone, the bubble of spacetime around you that you can affect in your immediate future, is bent to exist entirely inside the event horizon. Therefore, you can no longer have any impact on anything outside the black hole. Eventually, you will be pulled into the singularity, where the tidal forces approach infinity, and you will be spaghettified, your very atoms being stretched out and broken apart. But is this story true? The classical theory of gravity tells us that there is nothing to stop us from crossing an event horizon, and that, because of this, all matter ends up at the center of the black hole, squeezed into zero volume. But that is the standard theory, which doesn't take quantum mechanics into account and may not be accurate. Truthfully, we will never be able to measure what is inside a black hole unless we discover new laws of physics, so perhaps this is all speculation. But there are theories of black holes that suggest that they are in fact empty. In other words, there is nothing, not even space or time, inside the event horizon. Instead, everything simply stops with matter becoming infinitely close to the horizon without ever reaching it. Think of black holes as being analogous to thin vortices in superfluids. Vortices occur when fluids rotate, and they can be very long and thin. Typically, if you have a bucket of fluid and you rotate it, the whole fluid will rotate, and you will see one vortex in the middle, but not with superfluids. A superfluid is a quantum state of matter that occurs when certain gases or fluids are very cold. One example is liquid helium, which transitions at around 2.5 degrees above absolute zero. At these low temperatures, fluids no longer behave in a classical way. Instead, they are quantum, and all the atoms behave like one big atom. When you rotate a bucket of superfluid, the whole fluid does not rotate. Instead, small thin vortices appear in a lattice pattern within the fluid, while the rest of the fluid does not rotate at all. These vortices are a quantum representation of the angular momentum from rotation. One property of superfluids, however, is that they cannot rotate. They are, in physics parlance, irrotational. They have no vorticity. So, what's in these vortices then? It turns out that the vortices have non-superfluid in them only. None of the quantum superfluid enters the vortices. Ordinary fluid that hasn't yet transitioned is allowed to rotate, while the quantum fluid does not. If, however, we cool the fluid enough so that all the fluid becomes quantum, the vortices do not disappear. Instead, they become empty. In other words, the vortices are holes in the superfluid. This leads to an analogy with black holes. Suppose that they are like the vortices in a superfluid, not in 2 but 3 dimensions, and, like those vortices when there isn't any non-quantum fluid, they are actually empty. It turns out that you can construct empty black holes using a special formulation of general relativity, Einstein's theory of gravity, called Ashtekar variables. These are the basis for loop quantum gravity, one of the candidates for a theory of quantum gravity. One of the interesting features is that Ashtekar variables allow the metric, which defines distances but also represents the gravitational field in Einstein's theory, to become degenerate. A degenerate metric has no volume, meaning that space-time does not exist there. In a paper published back in 1991, a theoretical physicist used Ashtekar variables to create a description of a black hole that looked just like an ordinary one outside it, but was degenerate inside. In other words, the black hole is empty. Since the metric becomes degenerate, that means that matter doesn't enter the event horizon. Instead, it effectively stops at the event horizon since the metric has zero volume inside it. Indeed, the notion of there being an inside no longer has meaning. Rather than passing through the event horizon, matter would shrink to zero volume, flattening out onto the horizon itself. The only use you can find for such a theory is that it fits well with the idea that entropy of a black hole is represented by the black hole's surface area. We know this from the famous Bekenstein-Hawking formula that relates entropy to surface area of a black hole. If black holes are empty, then it would make sense that their surface area is what matters, not their volume. Another area where this idea might be useful is in quantum gravity. The big issue with quantum gravity is that we cannot define what happens at the highest energies and smallest scales, partly because tiny black holes form. Gravitational coupling becomes stronger and stronger as we descend. There are other issues with gravity, such as having a large-scale description that doesn't make sense as a quantum theory either. If the universe is in fact riddled with tiny black holes popping in and out of existence all the time, however, and these black holes are actually holes in spacetime, it could be that they are quantizations of entropy, in the same way that vortices are quantizations of rotation in superfluids. Since entropy is equivalent to information, these black holes are the bits that make up the universe. Bigger black holes have more bits. In other words, the universe at these scales has no information except on the surfaces of black holes. And if that is true, then perhaps we are looking at space-time and gravity backwards, and it is an effect of this information rather than a cause. According to holographic gravity, this unit of information comes not from space-time at all, but from entanglement between quantum matter on the boundary of the universe. Space-time is merely a projection of that entanglement entropy, like a hologram. It is meaningless to talk about what is inside the quantum black hole, since it is merely a dense information storage unit. Also, it is meaningless to talk about gravity as a force, because it is simply a holographic representation of information. At least that appears to be the most fruitful definition we have so far. Whether large, stellar mass black holes are empty is open to debate, and we will never know for sure. It could be that only at a certain quantum level are black holes actually empty, in the same way that superfluid vortices are empty of quantum fluid, but not ordinary fluid, when the superfluid has not fully transitioned. Again, we'll never know. What we do think we know is that black holes are critical to understanding how information is represented in our universe, and that the way our universe appears to be may be just a projection of a deeper reality that is pure information. In a later paper, Bekenstein mentions that it is difficult to come up with a solution to Einstein's equations where an empty black hole, a black hole with a degenerate metric interior, forms. Thus, it seems likely that stellar mass black holes are not empty. He does mention that two colliding beams of light might create one, however. Thank you so much for watching. See you again in the next video. Until then, as always, keep looking up, stay curious and dream big.